we go. All righty. Good morning. Good morning, Stanley. This is relatively short. I've only got 2.5 pages of notes. So that's got a backup beeper on it. Maybe I'll just kick the door closed. That helps. There, I'm cleaning a hallway. So, see how long I last this week with these things. I want to just sort of start up with triangulating pentagon. Just to do it, and so if I when I triangulate the pentagon, I get 3 triangles in it, and I just I obviously started here and just ran a line out everywhere. But the thing about pentagons is if you do that from any place, you get 3 triangles, because really once you draw a diagonal, you don't have any choice on where the other triangle is going to lie. So there's 3 triangles that come out of the deal. If I look at, I've got I believe this is I think it's an octagon. Yeah, it looks like an octagon, sort of. So if I triangulate this, there's a couple ways I can do this. If I just focus on shooting out diagonals from one of the vertices, it winds up looking like this broken glass kind of thing. But I get one more. But I get 1, 2, 3, 4, 5, 6 triangles. I'm going to triangulate it a couple of ways here. If I can draw it quickly and semi-decently. So there's, if I triangulate like this, so sort of zigzaggy on it. The same sort of thing happens. There's 1, 2, 3, 4, 5, 6 triangles. But we have a very different kind of triangulation here. With the pentagon, you're pretty much, once you pick the point, the other, or rather, once you pick the diagonal, the only other diagonal that's involved also had to emanate from that point. Whereas over here, that's clearly optional to shoot everything out from the same vertex. So I guess there's 2 things here. The first is something that we already know, and that is if I've got n vertices, then I get n minus 2 triangles in triangulation. We already knew that. We made use of that when we were looking at the art gallery problem. So that's not significant. But what is significant here is I have potentially different kinds of triangularizations. So the question here is, how many possible triangulations? you know, we can, just thinking about the octagon here, you know, I could do this from each of the vertices. So I've got, you know, I've got 8 different versions just of this triangulation. I can, you know, rotate this around also. But there are also some other ways that I can do the triangulation. So it looks like there's a lot of triangulations. And in fact, it turns out there really is. If I go to count, if I just focus for now on convex polygons, there's a nice friendly round shaped one. For a triangle, there's one triangulation. How do you say triangulation in symbols? How about triangulation like that? That's if I look at something that's got 4 sides, you know, I can triangulate like that, or I can triangulate like that. But that's pretty much it. There's 2 triangulations. If I move it up to a pentagon, so so I've got 3 sides, n equals 3, 3, n equals 4, 4, n equals 5. It turns out that you know, you sort of have this idea in different positions, but it doesn't take very long for you to rotate your way around to where you just duplicate something you've already got. So for a pentagon, that's probably the last one that I can draw reasonably well. You get 5 triangulations. So one thing that pops out at you is it's definitely growing with the number of sides, but it sort of stopped growing in a semi-predictable manner. If I go up to n equals 6, let me begin to try that. You get 14 triangulations. I'm kind of just about at the end of the focus here for where the laptop's sitting. For n equals 7, you get 42. N equals 8, 132. And it keeps growing, you know, making big jumps like that. So 429, I believe, is next. 1430. And you know, just dot, dot, dot. It keeps crawling up in a hurry. So, in fact, the next one is 4,862, and then it takes a jump, and pretty soon it's into 5 digits, and then 6, and so on. So that's for convex polygons, which it turns out, you know, are special for lots of reasons, but they're special for our purposes because they're relatively easy to think about. The deal with a convex polygon is, so thinking about triangulating a convex polygon. Man, the buzz is coming already. When I triangulate a convex polygon, think about sort of the way I attacked each of these. We picked the first diagonal that we're going to use in the triangulation. And once you've done that, you split the that diagonal splits the, so here's my polygon, and I pick a diagonal that I'm going to use in the triangulation, and that splits the polygon into 2 subpolygons. Because the original was convex, both of these guys are going to be convex. Let me give them names, A and B. So here's A and here's B. And because we were convex originally, A and B are both convex. So in fact, this analysis will just, you know, persist. I haven't introduced any additional vertices because I ran a diagonal across. And so triangulating A and triangulating B, and then, you know, using those two triangulations together will give me the triangulation of the entire polygon. So we can triangulate A and B and the combined triangulation will give us the overall triangulation. So then counting the number of triangulations that result from this one diagonal between these two vertices, I would count then the number of triangulations I could do for A and the number of so there's kind of, there's something that feels and smells a bit like recursion happening here. So the number of triangulations, how do I want to say this? The number of triangulations from the, give this diagonal a name, let's call it V to W, from the VW diagonal is going to be equal to the number of triangulations of A times the number for B. And so you know, so we multiply them together and we get the total number that we get from this one. But that was one diagonal. You know, I could pick other diagonals as well. I could just focus on B and look at all the diagonals that come out of it, or I could rotate around, but that was just one diagonal. So in fact, it looks like and in fact there is a relationship between the diagonal that was chosen and the number of triangulations I get for the overall. Let me just sort of semi-clarify that a little bit. It's really easy to see with some of the smaller polygons. Let me take a pentagon again. It's rather boring, but it gives us a sort of starting place. So I'll pick, let me take this as my diagonal. And when I do that, this sort of splits the problem up into a triangle, which is already done, and then a four-sided polygon to triangulate. And of course, then I can triangulate this two different ways. But that's you know, that's what I mean by this separation. Once we pick a diagonal, then if I move this up to a what did I do next? I guess I did a hexagon as the next example. And boy, that's a badly drawn hexagon. But you know, I can pick. I have several choices in what I can do here. One is I could pick this as my, you know, my first choice for the diagonal. When I do that, this splits it into a triangle and a pentagon, and then I triangulate accordingly. If I were to pick a different diagonal on that hexagon, let me just pick the next, move the right hand side down by one vertex. And if I do that, man, I must have quite a buzz going here. I didn't even come close with that one. So if I were to pick, so instead of just going and making a triangle, if I were to make this be my first choice, then the split here is into two four-sided or four vertex polygons. So you know, so there's obviously some the head count comes out a little different depending on which which diagonal I pick. Turns out that this is sort of a well-known fact. That has lots of different proofs and all kinds of different ways of realizing the same sort of thing before. So this is the fact that's interesting for us today. For a convex polygon on n+2 vertices, n+2 because, you know, we start with triangles. The number of possible triangulations the number of ways that we can triangulate that thing is 1 over n+1 times the 2n choose n. So I don't know if both of you have mathematical background, but I don't necessarily. So the when I write the binomial coefficient, the choose thingy, that's n factorial over k factorial times n minus k factorial. So it's, you know, it's it's something that you have to do a little bit of work to calculate out. But let's look at that value for some different n's. So so we're saying n+2, and the n then comes down into this. So if I look at n equals to 1, and we're talking about convex polygons on 3 vertices. So this is 3 vertices. That's triangles. And so we know that there's 1 triangulation. And so we ought to get 1 out of the deal. And so n is 1 here. 1 over n+1 times 2n choose n is 1 over 1 plus 1 times 2 choose 1, which is 1/2 times 2 choose 1 is 2 factorial, so 2 times 1. K factorial is 1 factorial, and n minus k factorial is 2 minus 1, so that's, you know, 1 times 1, or 1 factorial times 1. So I'm looking at, you know, the 2's cancel out, and we're looking at just a 1 out of the deal. If I do that for n equals 2, so again, we're talking about a polygon on n+2 vertices. We're talking here about, you know, 4-sided or 4 vertex polygons. So we're looking at, the formula becomes 1 over 2 plus 1, 2n, so that would be 4 choose n, so 4 choose 2. So this is 1 over 3, 4 times 3 times 2 times 1 over 2 times 1, that's the 2 factorial, and the n minus 2 is going to be, or I'm sorry, the n minus k is going to be 4 minus 2, so that's 2 factorial again. So I basically have a 3 factorial going on here. There goes the 3, 2, 1, and then 2 goes into 4. That gives me 2. And of course, with this guy, I have 2 ways of triangulating. Either one of those diagonals work. I'm going to do one more, just because I'm going to do one more. We do n equals 3. That's pentagon, right? And we know that there's 5 as a result that we ought to get out of the deal. So 1 over n plus 1, that's going to be 1 over 3 plus 1. The chooser is going to be 6 choose 3. And so I'm looking at 1 over 4, 6 factorial. And the denominator is going to be 3 factorial, so 3 times 2 times 1. And then the 6 minus 3 factorial is another 3 factorial, 3 times 2 times 1. And so we're looking at 4 factorial out of this, that nukes that. This is 6, so that nukes that, and we're left with 5 that comes out. Pick your favorite n and plug it in and count how many triangulations are for an n plus 2 convex convex polygon. Do these numbers look familiar to either of you? Stanley's going, yeah, I know those numbers. The number that we're getting here, the number of triangulations is it's a Catalan number. The Catalan numbers help you count or are the results when you count different ways of lots of other things in addition to the ways that you can triangulate convex polygons. If you think about parenthesizing, if you think about, so suppose I wanted to multiply together, x1, x2 up through xn. And if I thought about parenthesizing, the ways that I can actually perform this multiplication, it turns out that the Catalan number for n tells us a number of different ways that we can parenthesize that we can actually perform the multiplication. If you think about fully parenthesized multiplication, so like x1 times x2 times x3 times x4, fully parenthesized in that respect. So I guess the big point here is there's lots of ways to triangulate a convex polygon on n vertices. Like lots, if n is anything other than just a trivial number, we have lots of different ways that triangulation can come out. So a reasonable question is, what about non-convex polygons? Is there some way, some number that you can get by a calculation for non-convex polygons? The answer is, unfortunately, you don't. The best we can say is that the number of triangulations for a non-convex poly on n vertices is between 1 and the I guess I should say n plus 2 vertices, is between 1 and 1 over n plus 1, 2n choose n. So yeah, non-convex polygon on n plus 2 vertices. This is just smeared together, partially because I got my buzz going really bad here, and partially because I added stuff in there. In fact, I mean, it's even worse than that. For n greater than 3, there is a non-convex, I shouldn't say non-convex, there is a, it turns out it will have to be non-convex, but there's a simple polygon with one triangulation. And this is for any. There's
So that vary. You can have different numbers of, like you can have a different total number of triangulations depending
on the shape. Yep.
Yeah. Okay.
Yep. So like for 4. So here's the sort of pathological polygon of 4 vertices. There's only one way you can triangulate this sucker, and that's like this. Anything else is going to have a diagonal that goes outside, basically. So there's only one way to do this. So this is the unique triangulation for this guy. I fiddled around a little bit, and for 5, I believe it looks like this. And the triangulation is like that. It's like a bow tie thing. But it's a theorem. It's a fact that for any n greater than 3, you can always find somebody that there's only a single triangulation for.
Yeah, I guess the question I was trying to ask is, there's only that?
For
the non.
For this guy,
Yeah.
there's only one way
Gotcha.
to triangulate.
I guess what I was trying to ask is, are there any shapes where like you can triangulate it one way and get 3 triangles or 4 triangles, and then triangulate it a different way and get a different number?
No,
Okay.
no, that was that first fact, that
Right.
you always get n minus 2 triangles in triangulation.
Okay.
And hopefully that holds up here, right? If I didn't screw up these drawings, yeah, we got, so n is 4 here, we got 2, n is 5 here, and we get 3. Yeah, so you get some number between 1 and the Catlin number. The takeaway out of this is, first of all, it's it's kind of unfortunate that we can't say anything more concrete than this range. But the second thing to take out of this is that, in fact, the convex polygons yield the maximal number of triangulations. So anything that's not convex is going to have won't have any more than the Catlin number. So convex is maximal in that respect. That's all I got for today. So I'm sorry, we didn't even make it an hour, which is probably good. I've got just a hell of a headache. I don't think I'm going to be able to continue to do this whiteboard business much longer without some other way to breathe. So we may wind up with a different, may wind up trying to do something else here. I'm gonna, my brother-in-law says he has a very silent box fan. And so I'm gonna bring that in tomorrow and try that. And I think, with this microphone in the position it's in, which I hope is working for Stanley, I think I can maybe isolate the fan by putting it like someplace back out of the microphone's cone, and maybe I can get some relief. If that doesn't work, I don't know what we'll do. one thing that somebody suggested is I might go to using the screen and the Elmo over here and like writing on something in the projector. I can't just flip through slides, so you know, you're not going to see death by PowerPoint. I got to be doing something when I'm trying to lecture, or I can't do it. So but something's going to have to change here. To tell you the truth, it took me until Saturday afternoon to get straight last week. Friday, Wednesday, Thursday, and Friday of the non-toxic fumes just hit Friday. So in any event, we're going to be, something's going to change here. The last thing I want to talk about, I posted the programming project late Saturday night. Seriously, once I got straight, it just kind of clicked out for me. But it took a while to get to that point. I don't know if you've looked at it. It's triangulation by means of ear clipping or ear removal. It's actually fairly easy. The main tool in the process is the is-ear function, where you like feed it some vertices and it tells you if you've got an ear. And of course, to do that, you have to do a check of everybody else to see that that there's not an incursion into the ear. So that's actually all there is to it. The only other thing that's involved in it is how do you manage the vertices, or how do you manage what's left of your vertices? We have to keep all of the vertices around, so in order to perform that ear check. So that means you've got to have a set of vertices someplace. I just used an array and just kept the array unmolested as I went through the process. But in the clipping process, you take somebody out. Every time you clip an ear, you remove the tip of the ear. And so that sequence of vertices that goes counterclockwise around the polygon is going to change. So that means you have to keep a separate set that has the remaining vertices in it. I found that a queue is just made it trivial. And even just the really restricted queues that we used in CS2, where the only access that you could take something out was at the front, and the only place that you could put was at the end, and you could only destructively look at the front, so it amounted to dequeuing. That was sufficient for this. If you do that, basically, we care about predecessor and successor as we walk around the polygon, and you can get predecessor, current vertex, and successor vertex, all by just being careful with what you do at the front of the queue. I mean, the deal is we've got the vertices of our polygon in counterclockwise direction, or in one direction. Without that, then the business of identifying an ear becomes really problematic. And so, but if we've got them in order, then it's really just a matter of, I'm going to consider these guys, see if they make an ear. So we're looking at VI minus 1, VI, and VI plus 1. That little triangle, is he an ear or not? And if he is, you clip him out, and by clipping that out, you would remove this guy out of the mix. So basically, this would come out, and the polygon would then, this uninteresting polygon would then, would go from n vertices to n minus 1 vertices with a new edge in it. So with the queue, that was really easy to do. And I used my CS111 queue that made me DQ and then DQ and then DQ again, and use the middle one as the current ear. And then if you clip that out, if you if you clip that center one out, then you just, you know, NQ and NQ and cycle around the thing. That wound up being kind of nice because it avoided the situation where you kind of have all of your triangles emanating, or most of your triangles emanating from a single vertex. It avoided that. Then I got to playing around with it, you know. So what if I didn't destructively? What if I allowed myself to peek? So here's the front of the queue, here's the one behind the front, and here's the one behind that. What if I allowed myself to peek one back? So I would destructively get this one and then peek to see this one. And then since this had been destructively yanked out, this is the one that would have to then go at the end of the queue. That sort of changed the shape of this. I mean, you could get something that wasn't all just a fan out of a few vertices. And then I looked at what if you just, you know, like totally cheat and, you know, peek too deep. Well, you could get some different behavior as well. But that was just modifying the simple queue that I had from, I guess we used it in 305 also. And then I got to looking, in the standard template library, of course, has a queue in it that everything is all written for. You just have to specify the data type, and you know, and away you go. So it became really easy. Stanley, I suppose you guys did queues when you did the data structures course, so you probably have a good one laying around. If you just adapt it so that it can handle points, it should be really a piece of cake to do this project. Like I said, the only part that took any serious coding was the check for to determine if something was in here. So that's what I posted on Saturday night. It shouldn't take you more than a couple of days to write it. What I'm working on right now, I posted a bunch of data files to go along with it. What I'm working on right now is I kind of wanted to watch the triangulation of the non-trivial polygons that are out there. And so I started hacking on a little program using CMH to just, you know, draw the lines. And if I get that going, I'll post maybe a video of the triangulation process, or maybe I won't do anything except maybe post some of the triangulations that come out. But that's what I'm doing today, if I don't have to fix my girlfriend's dryer, which appears to have cast a belt off. But that's all I got for today. Sorry, guys. See you, Stanley. I hope you're having fun in Iowa.